to address in person, also when I sent a message around, we're asked a few weeks into the semester, every professor who's teaching a 100, 200 level class is asked, 300 level class is asked, hey, do you notice anything? So are people missing? Are they not doing all the assignments? Do you worry about a student for whatever reason? And so we're asked to flag everybody. If you're flagged, that doesn't mean I think you're failing the class. That is just more of a, hey, we should talk to the student, that students should talk to their advisor. Is there something that we can do to make this go smoother? Right, so this is a U of L-wide, you've probably heard about this, but it's a U of L-wide thing to flag students where you know from previous years, oh, if I see no in-class assignments in the first few weeks, then I need, somebody needs to go check up on these students. So it's a checkup. It's not saying that you're flagged for failure or anything like that. You're doing fine. We're all fine. If you just keep at it, you'll pass this class, no problem. I flag people because I'm like, oh, I'm worried about this. All right, so. Sorry, I'm getting blank looks from the entire room. So I'm like, no worries. I just flagged everyone that I was like, let's check upon them. I flagged pretty generously just to be on the safe side. Okay, I'd rather have you have one extra conversation with an academic advisor rather than me letting you slip through the cracks. Okay, so second day, we're going to go use the planetarium in a bit, but we're talking about the night sky and celestial coordinates. Celestial coordinates is basically, if you want to know where you are in the dome, or basically on a sphere, you need to measure two things. You need to know where you are on a sphere, which is different than a map, right? So how do we do that? What are the conventions? Oh, Moana's completely invisible, right? But we had what was Moana trying to do here? And this is she measuring the angular distance, the altitude of Orion, indirectly her position, or all of the above? Do you remember what she was doing? Voting in 1, voting in 2. I'm going to just reiterating this one so to make sure that everybody has their voting cards ready. Voting in 3. You can answer anybody change. No, this is mostly D. Yes, she's doing all of the above, right? So one of the things you can do is measure a difference between, for example, two stars on the, I have a convenient dome here, and you can measure an angular distance. So this is how many degrees are there between those two stars, right? You can sort of measure that with your fist or your hand, or you can measure that more precisely. But you can also measure how big something is, and typically that's only something that we have to worry about for the moon or the sun with our own eyes. But that gives you a size on the sky. So this is the angular diameter. So for the sun and the moon, what changes? Their angular distance, their angular size, or both? Voting in 1, voting in 2, and voting in 3. I got, the room's divided. Okay. So, you know what that means. You have to turn to your neighbor, even if the two of you agree, explain to them why your answer is correct. You've got 90 seconds. Voting in 1, voting in 2, and voting in 3. Okay, some convincing is happening. I'm seeing both angular size and angular distance between the sun and the moon changes. Well, the sun and the moon's angular distance, we saw that on Tuesday, definitely changes, right? There's a full moon that's 180 degrees, or it can be quite close together, right? So the distance between these two things changes all the time. But the angular size of the moon, does that change much? Not really, right? It's the same disk size on wherever we look at it. The sun, same thing. The distance between the Earth and the sun and the Earth and the moon, those distances don't change that much. So they're always the same size on the sky. They might look different, but that's an optical illusion, right? Especially if it's low and you've got like a flat landscape and it's sort of like a road that's going towards it, your eye makes this bigger. But the angular size of the moon and the sun stay the same. So what changes? Only their angular distance, not really their angular size. Yes?
So I think I'm just confused because they're both like pointing to the same thing, like the angle. So you're saying that the angular size is like how big something looks?
On the sky, right?
Okay.
So angular size is how big the disk of the moon or the disk of the sun is on the sky, right? So it's about a degree across, or 10 degrees across, I think. But I can't remember. It's about a pinky, no, you can't just block out the sun with a pinky, you sort of need a thumb, so it's about 2.5 degrees on the sky, the diameter of the sun, or the diameter of the moon.
Yeah, I was just, because the arrow, like the angled arrow is like pointing to the same thing on both.
Okay, so it feels like, yeah, there's this angle between them, right?
Yeah,
Yeah. This is the angle between these two stars.
right.
Yep. This angle here is the difference between the bottom and the top of the moon.
Gotcha.
So that's the bottom and the top of the moon. That's the size of the thing on the sky, right? So for example, the constellation can be the same, is a certain size on the sky. Those two stars don't move. But for example, you can have the difference between Mars and a background star. That changes all the time because Mars is moving. So you can have an angular distance between one thing and another. Is it fixed, or does that can change depending on if it's a moving thing like a planet? And so with the sun and the moon, their angular distance, where we see them, changes all the time, but how big they are stays the same. Are we on agreement with that? Okay, so or is it just you and everybody else has sort of dropped out of the conversation? No, okay, we're seeing some nods. Okay, fantastic. So the point is that we talk about distances, like angular distances, when we want to go from, for example, okay, we're here, and I now need to go to the next star. Then I know how much difference I need to, like how much I need to change my telescope position. But if I want to talk about angular size, that's like how big it is on the sky. That doesn't tell me how big it is in real life, because that physical size, like how big of a thing it is, because then I need to also know the distance. And so if I want to know the physical distance, like the angular distance is the physical distance, how far away it is, the physical distance being the physical size of the thing divided by the distance to the thing. And so, and you have to make sure that those are in the same unit. So if I want to make sure how big something is in real life, or I, for example, know that the moon is this many kilometers across in diameter, and it's this far away, I can figure out how big of an angle it is. Basically, small versus far away. And so when we talk about positions on a globe like this, so when we talk the angular distance between two positions, we use the North Pole. The South Pole, we basically took the Earth's longitude and latitude and projected it onto the sky. So the North Pole is, plunk right there in the center of our at the top of our sphere, and the South Pole in the bottom. So we just projected our own Earth coordinates onto the sky. And there's a reason for that, because the North Pole neatly stays in the same spot as the Earth rotates around it, under it. So we have the North Pole, the South Pole, the equator here. There's a celestial equator, and then we have lines of longitude. Those are these ones, and so the line of latitude, those are the horizontal ones. Longitude, latitude. Who's heard of longitude, latitude, or is everybody GPS? Fantastic. Either because Google actually says longitude, latitude when you drop a pin, it's kind of awesome. So yes, we took that and projected that onto the sky. So we have the North Celestial Pole, the South Celestial Pole, we have a celestial equator, and then we have lines of declination and right ascension. So the equivalent is right ascension along, basically along the equator, and then above the equator, the number of degrees to get to declination, or negative degrees if you go below the equator. So if I want to know where something is on the sky, and it's not, if it's not moving, I don't have to specify a date. If it is moving, I have to say, like, when is it where on the sky? So I can say, this particular planet, for example, is at right ascension, this number, declination, this number, on this date. That gives me a position on the sky, right? I only need two numbers as long as I crawl along the dome to know how to get there. And my 0 point is one of these right ascension lines. That's my just arbitrary pick. So 0 point, so I can say, like, okay, it's minus 89 degrees this way and 36 degrees up. And then I know where my thing is, right? I project it onto the sky. Yes? Because, yes?
So would all like line and longitude be only line position, or would only
Sorry, can you repeat that, please?
like would all your line and longitude be all the line position, or would it just be like you right
Oh, so this is the line of right ascension. This is the same right ascension. That is the same like line of longitude. So longitude is like, this is all the same longitude, and it's the same number of degrees along the equator to that line. Yeah. See, this is one of those things, like, did he just give me a thumbs up because he thought it was okay, or did he do what? It's one of those, like, do you get it? I mean, if not, then tell me, okay? And so the reason that we do this is because, you know, we keep rotating underneath. So having a celestial coordinate system means that, like, okay, this is the position. As long as I know where north is, and as long as I know what time it is, I can sort of follow along to which the right ascension and declination need to be. So right ascension and declination are the two things that are always reported on any astronomical object. Anything that's new is like, this is where you find it. And it's with respect to the north celestial pole, the south celestial pole, and this is the right ascension or declination. And so to the point that if there's like a real competition happening, people blanked out the right ascension and declination until the last minute before it got published, because like they didn't want somebody else to scoop them and like go look at that position just before. But because everything rotates and we're basically rotating underneath, the sun, the planets, and the moon appear to move when viewed from Earth, right? So you see, if we take a long exposure, you see stars, you get these star streaks as we rotate underneath. And so we also have a coordinate system for what we see overhead, right? So this is not the coordinate system for that we've made basically expanded on from the Earth out. So if we're looking, this is what I'm looking at right now. So it's an inverted mixing bowl. I like this because it has all the speckles. And so if I'm looking up, and then here we've got Earth, we've got the equator, so here's this Earth equator, and here's like the celestial equator, here's the North Star, so that's where the North Pole, the celestial North Pole is. And so I see stars rise in the east and then set in the west here, and rise in the west, set in the east. I always get this wrong the first time I say it, I don't know why. And so you start here, the star rotates around this way. So it starts here, it is at the highest point here at point 2, and then sets again at point 1. So, but because the Earth is, like, here's our observer, right? Here's our fabulously pointing man, and there is a planet underneath him, so he can't see straight down. He can't see any object down here. There's basically a horizon, and that horizon cuts off a chunk of the celestial sphere. So you can only see the stuff that is above the horizon as it rises, peaks, and sets. And there are stars, some of the stars that are close to the North Star, they actually rotate, while they're rotating, they're basically visible throughout. So they're always visible, and then there's ones that are that rise above the horizon and set again. Did I lose everybody? Not lose everybody. Okay, right. Okay, so there's two parts that we can see. Sorry, there's two things, right? There's the coordinates on the celestial sphere, and then there's the ones when can I see something overhead. And so that horizon is the horizon shown a real physical horizon or an imaginary plane that extends from the observer out into the stars? It's the real horizon or it's an imaginary plane. What do you think? Voting in 1, voting in 2, and voting in 3. Almost equal mix. Yeah. All right. You know what that means. That means you turn to your neighbor, and even if the two of you agree, you have to explain to them why your answer is right. Got about 90 seconds, or basically my last time.
Imaginary.
Okay, this side of the room turned red. This side of the room has a difference of opinion. All right, let's take it from here. This is everything that he could potentially see, right? There's no Earth, at least in the way. You can imagine that unless you live on a perfectly flat countryside with no trees, no buildings, and nothing else, there could be other things in the way, like mountains or buildings and trees or what have you. So it's not your real horizon, it is a horizon that's idealized. So it is the thing like, yeah, it's technically up, but you know, the CBS building is in the way. Or it's technically up, but that's where a mountain ridge sits. So it's up as in, yes, it should be over the absolute flat sphere of the Earth, right? It should be over your imaginary horizon. You always see less than the perfect horizon that's being used for whether or not an object is up in your, well, just about any app, right? You have like these apps which you can look like what's up on the sky. It's really neat and convenient, but some of them go like, yeah, you should be seeing that, and then you look over and it's like, oh yeah, but there's trees and stuff in the way. So it's never your real horizon, it's always the theoretical ideal. So can an observer see more stars, less stars, or the same implied by the horizon? Now that you know it, I've explained this. Voting in 1, voting in 2, and voting in 3. All right, well, I think B, yes, like if there's stuff in the way, I mean, you could be literally sitting in a canyon or something like that and go like, well, I see 2 stars straight up, that's sort of the worst case scenario. And everything else is sort of obscured. So, can an observer see an object located below his horizon? Voting in 1, 2, 3. Yeah, absolutely. Yes, thank you. All right. So, if there's a star that's unobservable in a position, is it star A in position 1? So here's star A, position 1. Star B in position 4. Star B in position 1, or star A in position 4. So which one of these is unobservable? 1, 2, and everybody's got them up already. Fantastic. Yes. When a star travels from being below the observer's horizon to being above the observer's horizon, is that star rising or setting? 1, 2, 3. Yes. Star rises. And so in this case, see which way this guy's pointing. What direction is the observer facing? Towards the south, towards the north, towards the east, and towards the west? What does he looks like he's facing towards? 1, 2, 3. Yeah, he's facing north. Okay, so where would the observer now have to look to see the star indicated by the arrow? So high in the south, northeast, southeast, high in the northwest, and high in the southwest. One, two, okay, time to talk to your neighbor again. So, turn to your neighbor, even if the two of you agree, and discuss why your answer's right. Let's say them. 3. Got a new uniform A, so let's see what was A. Northeast. I'm glad that everybody thought east, right? Because it's rising to the left, and everything rises from the east. But north is this way, that's behind him, and so he's facing towards the south, right? And like, this is why I did this question first. If that's behind him, then, and this is east, due east of him, that means it's in the southeast. See, it's pointing south. I know we all got it wrong. I always have to remember, where does everything rise? It rises in the east. And every time I'm in front of this room, I just poof, forgets out, goes out of my brain for a minute. Yeah? Okay. No. Okay. It's like if I hear yeah and then I hear like one no, then like does stop. Okay. Yes.
So is it only south because he's facing away from north?
Right. He's facing away from north, but it's like okay, so it rises in the east, and it's like this way is the South Pole, right? So this way is where the south part of this on this compass points. So if it's at the highest point, it's at the it's the highest point, but south. So this is what I now do. It rises here. We're all this little guy, right? We're all facing north is behind us, and the star A rotates up, starts here, rises, and it's at its highest point, and sets. So our compass heading says north over there, because the north star is behind us, it's shining on our back of our heads, and that means our compass is pointing south on the horizon here, and that means it starts in the east, is the highest point at due south, and then sets again. Does that make sense? If I pointed on the sphere rather than on the, yeah, it's, sometimes I've noticed that people like have trouble with the illustrations, but it's not everybody, so it's okay. All right, so as we're standing in the field, like we put our back towards the north, and this is the line from north to south, so it's literally the line from, make sure that I don't move through with the laser, all the way over our heads, right? So that is called the meridian. That is the point of where that's the highest point is as things rise and set in the sky, that they'll hit the overhead, like that's the highest point. If it's directly overhead, so it's directly over our heads, that would be this thing here, that's called zenith. And so if something goes through zenith, it's directly overhead. So if you're at the equator here, then the sun can go directly overhead. And that's a funny moment, because that's the point where your shadow is literally a little puddle of darkness between your feet. There's no shadow because the sun is directly overhead. So zenith is a special spot. And so if you're trying to observe, for example, a particular star or planet or galaxy, if you can find somewhere where it's directly overhead, you have the least amount of atmosphere between you and your observation. So zenith is awesome. And so everything starts off in the east, rises until it hits the meridian, and then sets in the west. Here it's the sun, does the same thing. So on the winter solstice it's low, and at the equinoxes it starts due east and due west, and then in the summer it starts even further north, so it's like it goes almost towards zenith. So you can track things basically as they rise and they go through the line above you. So there's two ways that we think about this, right? We can think about it as where on the celestial sphere is my thing, and that doesn't change unless it's a planet. But you know, if it's a star, it'll stay stuck there. Like that's my position. If I want to communicate to an astronomer in South America, I say like right ascension this, declination that, and they know where to go. Then they go out in their field, set up their telescopes, like right, where do I look? Because that now depends on where exactly they are, and so where in the where on the planet they are, so how far above their horizon or how close to their zenith they need to look. And so with telescopes, it depends on where you are and you know when to point to the right object. So we've had a common way to define where things are on the night sky. So there's such a thing as called as an astronomer's telegram. As you can tell, that has been around for a while because telegrams don't exist anymore. Trust me, I've tried to send my friend a telegram just because it's so old-fashioned, but you can't. And so there's something called an astronomy telegram, which is essentially an email now, and it says, oh, we found new thing at right ascension this, declination this, brightness this, everybody go look. If you're interested in these kind of phenomena, go look. That can happen that you have some really funny mistakes because a few years back, a colleague of mine in South Africa sent around an astronomy telegram saying, oh my gosh, new nova at right ascension this, declination here, you know, everybody go look. And then there was like 30 minutes later, very sheepish, like, oh no, never mind, it's Mars. So, you know, because that's something that moves around and that wasn't there the night before. It's like, yes, you found something that wasn't there the night before, but we've known about it for a while. And so having these things is, it's useful to have the position over time, like to know where these things are. But as you need to know where you are, what time it is, to know where on the dome above your head you need to look. See where the difference is here? Checking for the occasional nod just to make sure that I haven't lost the entire room. All right, and so what happens over time in the northern sky? We've got Polaris here, and if you're far enough north there, you've got the Little Dipper, so it's the little tail of Little Dipper, and you've got let's see, Big Dipper here, and so if you look at the edge of the pan, I think of these things as frying pans. I mean, they look more like frying pans than bears to me. Especially since bears don't have particularly long tails, so if people go like, here's the tail of the bear, it's a really long tail for a bear. Anyway, so I find the frying pan, I find the front part of it, and if you basically take this distance and take it 5 times, and you end up at Polaris. I'm saying that because this is pretty easy to spot. Little Dipper is a lot fainter, so it's harder to see, but it's a good way to verify. Like, yes, that last one, that's Polaris, but Little Dipper rotates around and the Big Dipper rotates around. So depending on how north you are, you can actually see the Big Dipper anytime during the night because it rotates above the horizon. It's a circumpolar star. And so when you get those circumpolar stars, they're always visible. And so if you, for example, look at this, look at that, this star went all the way over here, and like this star went all the way over here. Here's a question for the room. How long did it take that exposure? Like, how long was that exposure? You can sort of tell from the star frame. Like, how long was, let's see, this guy goes all the way over here. So how long is that? full night. Okay, try to give your answer in hours. Like, guess how many hours this is. Yeah. 24? 24 hours. We've got 24 hours, yes. 12.
I'm gonna say 6 hours.
6 hours. Okay. 8. Nice round numbers. Thank you. If you remember those. All right. We've got 6, 8, 12, and 24 hours. Okay. So how long would it take for a star to rotate all the way around? 24 hours, right? That's the 24. Okay. So if it's at almost half the time, we get to 12 hours. This is a full 12-hour exposure of the night sky. So you can, that's a really long time to expose a single photograph. But so if you look at the North Pole and you just have a nice long winter night, you can actually expose for almost 12 hours. From return when we do the worksheet. So which one of these stars is a circumpolar star for observer 1? So she's standing right here, is observer 1, observer 2, and observer 3. And so A, B, C, D. Which one of these is a circumpolar star for observer 1? Photon 1, photon 2, and photon 3. All right, yes. So if observer 2, do you draw the, which one of these is a circumpolar star? Photon 1, photon 2, and photon 3. She doesn't have any circumpolar stars. This is a mean question. This is not something that will appear on any midterms because there's no good answer. This one will literally start and set overhead, and she can't see A. So if you're at the equator, you can see circumpolar stars. There are no such things. And so observer 3, which one is a circumpolar star for her? Photon 1, photon 2, and photon 3. Yes, we got it, right? So the ones that are close to the, how long did we take that picture? Okay, so last question. What's the direction of the observer facing in this picture? Which way are we looking here? Hint, this is Arizona. So we're in Arizona. Which way are we looking? Photon 1, photon 2, photon 3. Yeah, we have to infer some things here. All right, I've got blue, red, yellow, green. Okay, I don't look at every answer here in the room, so I know what happens. You turn to your neighbor. Even if the two of you agree, you're going to explain your answer to them. All right, let's do some smoothing.
There's two things that can't be and two things that can. So that's kind of a trick question. You could be looking this out. I'll take that. I feel like I've seen that exact route before.
Yeah, that's what I'm doing. Making sure that those are the answers, because I've noticed that if I give the answer, people just kind of hold on to them and wait for the answer to appear. Okay, let's see what I can say. But I noticed that if I do give the answer afterwards, that's where I noticed that people start not giving the answer. We will run through all of them for the midterms, so I run through most of these questions. Practice. All right. Let's vote again. Sorry for the delay. 1, 2, and 3. I love when a good discussion happens, because I've got majority North, okay, two hints from the picture. Stone Arch, that's Arizona, so we're in the northern hemisphere. Two, all the stars seem to be on circles, circling around here. So everything is rotating around that point. Well, we only want to know one point in the northern hemisphere, but that does that. That's due north. We're looking due north at the Polaris at the full stop. So, but I know when you get a question like that, you go like, it feels like those brain, like, wait, am I missing a piece of information? It's like, no, you have to look very carefully at the picture. Okay, so we have a night sky group work, and it's just about, when stuff sets and starts. If you've got a few extra, let me know. Still bad at handing these things out. So what I did with you is that I feel like I'm just answering something classic that just did, but so you don't have to memorize equations, but those are in the back of the key is to, even if you have no idea how to do this, maybe it's this kind of problem, to then put that right in there, so you know that at least you thought in the right direction. Maybe someone will get close to it. Always goes wrong. shut down for no reason, so.
Yeah, we're just, they would think that sorry.
It's a fun room, but it's a little hard to talk to the people.
They both think that this walls are going this way, like around, but I was thinking this way, and we're just having Right, and they're saying that because this is like up, they would go up. So we're just like the orientation.
So, pointing north.
Yeah.
It's in fact that way. So pointing north, everything rises in the east, sets in the west. So yes, it circles one around like that.
But which way is, like, it's hard because this is like circling around, but it's on like a different plane. Like, because if this is north, it does rotate around, but so are we like here, and it's like, okay, it's gonna go over us.
I'm putting the star on the North Star, right? This is my horizon on right here. I'm seeing like house, trees, everything. West is over here, east is over there. It rises in the east, and it sets in the west. So everything rotates around like this.
So you're saying the arrows go above, that just doesn't make sense to me, because if you're saying that's the north, then the circle being on this plane would be like, okay, then here's north, here's south, and the stars are going around like that. So like, that's why
Okay, so
you're like, wait, no, that's not.
you have the two things, right? The hint is the fact that I'm seeing trees and houses here. So we have where are things on the celestial sphere, and that's how we get started. That's where we say, okay, it's close to the celestial sphere, celestial north, for example. But what am I seeing if I stand in the field? I'm seeing like, here's Bob's house, there's his trees, right? This is what I'm seeing.
Okay, so you're saying, because this is the horizon.
That's our
So
horizon.
that's it rising.
And it rises over the horizon.
Okay,
This is
okay.
what I'm seeing here right now. Like, it's very specific for the spot that we're at.
Okay.
And, okay, I think you got it. Figure out which thing we're looking at.
That's the whole day. Yeah. And then looking at it, yeah, I mean, I guess I see what you're saying.
How are we going here? Sorry, I got distracted by laptop shutting down, but I usually try to walk around and do that.
So how many hours is that plus the cutoff? The horizon dot cutoff. That star is short, the star short. So this one would be the rest. See, that's what I was thinking. But that one seems like it would be not very long.
Yeah, this is what three days on the show.
This one kind of thought you would get different.
I was getting ready to leave. How's everybody doing? It's a thinking question, but I think I'm seeing phones being popped out for non-checking reasons. Okay. Yeah. All right. Who recognizes this shape? Who's seen this on the sky? It's Orion, right? This is the winter constellation. It's a good one. And it's really helpful because this is the only time, so if you're looking at night, your eyes darken out and you use your rods in your retina most. So you actually mostly see black and white, right? You darken it out longer, but basically you see in shapes of, detecting color is really hard. all the stars are essentially white-looking, with one exception. And the neat thing here is that because you can look at either corner, you can compare the two rather easily. And you notice that this one is a little blue, and that one's a little reddish. And the reason that I want to point that out is because now you can point that to your friends out, like, okay, here's the three that I recognize as the belt of Orion, and that one that's in his armpit is Betelgeuse. And so you can now point out Betelgeuse to as a party trick. And so Rigel and Betelgeuse are two different temperatures. We know this now because we've learned about black bodies, right? How light gets emitted. And that means that Betelgeuse is cooler than Rigel, and Rigel is a hot blue star, and Betelgeuse is a big red giant. And so we've got Sirius, the dog star, over here, and Aldebaran. And you kind of notice about these kind of cool sounding names, but Aldebaran is not a normal English word. All these words are essentially from the very first star charts that Western Europe got their hands on, which were from the Arab world. So a lot of our names for the various stars are now still the Arab names for them. And so Betelgeuse, for example, despite being an excellent movie and or play, is also an Arab name for that star. And so if you take from Sirius, you basically go along that belt, you can find Aldebaran, and then quite close to that is a little grouping of stars. You all have pretty good visual acuity. You can probably pick those out, even in the city, and that's called the Pleiades, and that is the nearest actual physical group of stars. They're all bluish, although it's really hard to see because there's not a nice red star next to it. And so they're all in a group of, it's a larger group than the 7 stars, but they're often named the 7 sisters, or let's see, okay. That's the wrong button. They're called the Pleiades. Often in many, they're the 7 sisters or the 7 nuns or something like that. And if you know anybody who drives a Subaru, you notice that their sign is a bunch of stars. That is the same thing. They're named after this group of stars. And there's a lot of stories about them, but I think the coolest one is this is all a group of stars that are fairly young. We'll talk about star formation, etc. soon. And they formed together, and they formed since the dinosaurs. So the dinosaurs did not see these stars. They're younger than the dinos, or at least most dinos. And so I like that fact, and so you can sort of see, if you extrapolate, you can find Pleiades. But this is much easier to do with the dome, so we're getting to that in a minute. So if you look at star charts, they typically look like this. So we'll talk about the little stick figures as well. And so now we're going to move to the dome. The special ones are, of course, the ones that our sun moves through, so that's called the zodiac. And so those are the ones that I'll highlight in a minute. There is an extra credit, so this is the thing that I wanted to tell before we move to the dome. There is an extra credit. It's like you take, for example, the Little Dipper, and in Arabic, in the Western, it's called the Little Dipper, and so they're the same. But as you go through the various different civilizations that sort of name these, and from whom we still have star charts, you can see that, constellations aren't the same. Different groups of people actually highlight different stars, or smaller groups or bigger groups of those stars, or in a different way, and they have very different stories to go with them. Fish Hook, for example, for Moana, or Scorpio in Roman world. So the extra credit opportunity is to go to this website, and this will be, it's on your, this is on the slides, that are posted already. But the extra credit is to pick a non-Western constellation and research it a little bit. Like, why did they call it Dog's Bone, or the Fish Hook, or what have you? And so you can have a look at that, and the figures in the sky talks about how the different cultures label different constellations, or the same constellations, with a completely different story. So yeah, if you want that, it can be really short. You can have a look at that. All right, now planetarium time, because I can see from the lines in the red light that we're all keen to go get this, to use this thing. So, all right, we are now, okay, facing south. Here, east, north is behind us, and then west is over here. And so, if we're going from the horizon up to zenith is 90 degrees straight above us. Okay, I'm the only one not sitting, so I'm going to carefully brace myself here with the thing. So here, for example, the sun is almost due south, so a little bit from here, and then almost 40 degrees altitude and alt-as. So if I'm talking about how far along the horizon and how far along from the horizon up to zenith, I'm talking about alt and as. But if I'm talking about where it is on the celestial sphere, I'm talking latitude and longitude, right ascension declination. Okay, I'm seeing some horizon appear, so you can see some trees here. So if I have something rising in the east, so if I've got something rising here, it might be hidden behind the trees for a little bit until it hits the meridian and then goes back. All right, and what's this green line here? That is the plane of the solar system. So the complicated thing is that nothing neatly lines up. Why doesn't nothing neatly line up? Because we're not on the North Pole, and our pole doesn't neatly line up with the pole of the, or our plane of the rotation doesn't neatly line up with the plane of the orbit. So everything is sort of at angles with each other. As you can see there,
And it's always moving.
and everything moves. Just to, keep it simple. And so, as you see over here, you see our familiar pattern of Orion rise. So here's the, 2 feet. There's his armpits. There's his belt. Let's not talk what that is. And so here's the combination of Orion. So that's the hunter in Greek, and it's often a hunting figure. It's like some human figure is sort of drawn here by most cultures, not all of them.
And that's his sword he hunts with.
Sure. I've never seen anybody hunt with a sword, but okay. And so this is, if you extrapolate that a little bit, like the next bright point here is Sirius. If I go this way, where did the Pleiades go? Help.
Yeah, I see them already. Oh, I have the power to stop this constellation, so I'll do that in a second.
Yeah, usually the night sky doesn't move this fast, which is good.
Let's put
because-
the top belt star right on the meridian for measurement purposes.
Alright. And then- So the angular size of Orion always stays the same, and then here we've got the angular distance is like from here to here, that stays the same because these stars sort of move together. But if I want, go for the angular distance between here and let's say one of the planets, that changes. All right, the angular. Okay. Is this it? Hang on.
Yep.
Okay. That looks like it. It looks like a little frying, like the world's tiniest frying pan. So if you extrapolate that a little bit here, then here is the Pleiades, and here is the V of Taurus, the bull. So as we look at these patterns, I'm going to go move very, very carefully to where Drew is standing because I can't do this without
Your neck will appreciate it.
my neck will definitely appreciate that. Everybody here is in a nice comfy seat, probably sleeping right now, but I cannot do that from right there. So, all right. So we started hanging pictures on the sky because basically this was the light show that you got if you were a hunter-gatherer in the savannah, or you were on the bison on the tail or something like that, or you were just living in the Euphrates River, and it gets pretty dark at night, and so you have all these fantastic pictures, and so you can actually sort of hang your lore, hang your mythology off them. So this often became a hunter, and this V became like the animal that he was hunting. But I've also heard one where, let's see, if I remember correctly, there's a couple of lions over here. This is the hunter, and this is his spear. So basically his spear is on the far side of the lion pride, and these are all his wives that are sort of poking fun at him. So everybody made that was an African story. So there's all these different stories using the same dots of light, because if you can see them, you can use them as sort of the help for your stories. All right, so we have the constellations, and Orion, you'll never meet anybody who is an Orion, because this is not a part of the zodiac. So there's
the stories.
There's the stories. These are the stories from Greek and Rome. So you've got the big bear over here, and you've got a little bear over here. And so you've got Taurus, which is on the line, the green line here. And the green line is where the sun moves during the day, but also all the planets move, because this is the plane of our solar system. So this is where everything that moves along. So if, say, Jupiter is in Taurus, that means that Jupiter is basically sitting here. Mars is currently in Twins Gemini, right? So these are positions along the path where all the planets, the wandering stars, move. And so those are the ones from the zodiac. So yes, you will never meet anybody who's an Orion, because it doesn't intersect with the zodiac. So why do we call somebody why is somebody Gemini? It's when the sun is in that constellation on the day of their birth. So you can't actually see it, but the sun's there during the time that they were born. Here is Cancer, the crab, lion, Leo, like the lion. So another thing, they're not equally spaced, right? So the sun doesn't spend an equal amount of time in Gemini as it does in Cancer.
Zodiac and the sun.
Here we go. So here's Leo. Yeah, you see this and you immediately go, that's a lion. But people hung their stories on it, right? So you can see maybe Cancer being this tripod. Gemini, okay, there's two things there. And so if you're on a particular day, so you're in September, you become a Virgo. And so we talk about timekeeping, like this is a way to keep the movement of the celestial sphere. Basically, it sets our day, we get the month from the moon, we get the year from our orbit. The seasons come and go, and using these, you can actually start figuring out where you are in the calendar. So timekeeping, and especially calendar keeping, was an early job for people who looked at the sky. So astronomers, when they say astronomers in Babylonian sense, these were people who were basically, you're in charge of keeping the calendar. You bring out when the major feasts and births happen. You give us a projection for when we should be sowing the crop, because look at that, it's let's see, we're right here, so suppose we're in May already. It's actually keep track of what day it is during the year. So and then they just sort of extrapolated that, maybe it's also important for individual people, not just for the season, for individual people. And you can imagine if you give the king one good prediction that you maybe get a pay bump. So coming up with, hey, maybe it's important if you're born in July. Well, it might be important for a generation born in July because the food is plentiful or something like that. But for individuals, not so much. But that's where the whole the idea of astrology comes from, right? So the fact that you were timekeeping, and it was a very powerful tool, having an accurate calendar, and either as a hunter-gatherer or as somebody who depends on agriculture. It doesn't matter if you know what part of the year it is. If you know if it's you're getting to September, and you go, the bison is late. If I know what calendar time it is, and I know that the bison haven't showed up yet, that's important. That's critical information. We've got to make whatever we have last because the bison is late. They should have been here already, but they're not. Right? This is stuff that you need to make decisions. So you can imagine this being very useful information, and then sort of taking it one step further. Maybe this is important on an individual scale. It's not, but this is why we have the zodiac still on, back in the newspaper, on all kinds of apps to tell you whether or not you should eat your salad. You should eat your salad. The stars have nothing to do with it.
Yeah, what your horoscope reader tells you is wrong by about 2,000 years now.
Yeah, no, also that, but it's mostly, look, I don't mind if you read it for a laugh or something like that. The reason that most astronomers get so high on their horse about it is because it's often used to swindle people, and I don't like that at all, right? So that's the part where I'm like, please don't use our pictures and the pretty stars and everything to swindle people. So that's why you get the reaction. But honestly, it's kind of fun to say, oh, I'm a Gemini. Like, it's an icebreaker. I'm not a Gemini, but you know, I'm along here somewhere. Not that it matters much.
Okay, let's go back to fun stuff.
Yeah. No ranting, right?
It's hard to see it, but there's a little red circle there.
Here's the red.
If I start time moving a little faster than the real thing.
This is a bear, in case nobody spotted that. I didn't. Here's its head, clearly, pointy nose bear. And this is the other bear, the little bear. And I've heard why their tails are so long, because apparently Zeus grabbed them by their tails and flung them into the sky, which really feels like a bit of a, we've written over this issue, but yeah. So they have these long tails.
I'm going to turn the trees back on. And the neat thing about the bear is even with some trees or your neighbor's house, it's still there a little bit.
You can spot this pretty well.
Like you're out in a field with no trees, it never sets in Louisville.
So most of it is visible except for the last one, but most of this one you can find pretty quickly, and then you take these two stars and you sort of like extend that line, and that gets you to Polaris. That's a pretty bright one. The rest is a little dimmer, so you sort of look for that frying pan as a
You really can't see Polaris here in Louisville.
Yeah,
But
light,
you can, I mean, not Polaris, sorry, but Little Dipper.
yeah, light pollution is pretty bad. So if you've got lots of street lights and stuff, you know, no matter how good your eyes are, you don't have the contrast to actually spot these. So, but the darker you know, you've got a couple of really great state parks around, and they have good light control, so you can see a lot. If you are ever at sea, say in the middle of the Atlantic or Pacific Ocean, yeah, you have a fantastic view because there's nobody nearby to have lots of artificial lights. So,
And if the dipper's behind your neighbor's house, look up for the M or the W, it also points to Polaris.
yeah, so this is Cassiopeia, and I'm trying to figure out how to actually find Polaris from Cassiopeia. That's a little harder.
The seat of the throne is a triangle. Use the triangle, and there's another very dim star right there you won't be able to see, but just come straight out of the triangle. Wherever Cassiopeia's W or M is, come straight out of the triangle. To the brightest thing you see close by.
Yeah,
If
this
the
is-
dipper's up, you can always do it that way.
Serpents is hardly visible. You have to be a
Yeah,
really
you gotta be
bright spot.
somewhere really dark to see Draco the dragon.
Serpents are.
That's dragon.
Oh, okay.
Draco. This one is another throne. This is nicknamed the house for obvious reasons, but it's King Cepheus, Queen Cassiopeia on their thrones.
So you'll notice that these stars are visible no matter what, right? These dip just below the horizon, but around this circle, those are called the circumpolar stars. If we go further north, it's a bigger circle, so the whole bear is now visible. If you go further south, the circle gets smaller and smaller until only a few stars, and eventually you can't see Polaris because it's just above the horizon and no longer above the horizon. But these are the ones that are visible all the time, so this is why this is such a useful constellation, because basically you can spot that even in somewhat, you know, semi-okay situations, and then you can go, all right, oh, and there's north. Okay, that is my compass heading north. So you can imagine that Polaris was a very important star for most people who were navigating anything like the steppes of the Midwest to the Pacific Ocean, or the deserts of the Middle East, right? If you are trying to find where north is, if you can find that star, you know where it is. Now, because our Earth's axis wobbles a little bit, Polaris actually moves around, like our north actually moves around Polaris, but it is pretty much where, at the moment, where the celestial North Pole is. All right, so you can see certain polar stars, how everything rotates. This is what, 3 times the speed, 10 times the speed?
Oh, I don't know, let's see, it's,
30 times the speed, I think. Yeah, no, everything doesn't rotate this fast. I'm not sure if you've spent
I can't really
night
tell,
counting.
it's set for real time, but I'm using,
Oh, this is definitely
it's,
sped up.
0.79 degrees per minute.
Okay. So, if you, this feels like it's,
But yeah, if I do this, now it's real time. Now
So-
we're running in real time, and the sky looks like it will tonight at 9:30. So the dipper will be high in the sky right after sunset. And we have a full moon tonight too, just like you see up over your left shoulder.
so if you find Polaris, you've got your horizon, you can get the angle between the north, like the horizon and the North Star. That tells you where you are on the planet in latitude. That gets you the latitude. So latitudes were easy to figure out, like how far north on the globe am I? If Polaris is straight up, I'm at the North Pole. It's exactly in zenith. And so the distance between the angular distance between the horizon and Polaris gives me the position, one of the positions that I need to know on Earth. The other one is how far along am I along the basically the one that equator, the longitude. And longitude was such a problem that you need very good timepieces for that. Here's the funny thing. So in the 17th century, when you couldn't figure out, the West had real trouble finding their longitude because they couldn't make an accurate enough clock that actually could sit on a rocking boat. The Polynesians figured a different solution, which was basically find pairs of stars and see if they set on exactly the same point of the horizon. And so that would tell you actually what longitude you were at. So their lore, their star finding, had a decent way of figuring out if you're at least on the right position. So if you're like, oh, we should move south, and we should move, our course should be adjusted or not based on pairs of stars. And I thought that was a clever one because they gave Captain Cook a chart, like, here, this is how you navigate to Hawaii and things, and he couldn't figure it out. And later, the studies were concluded based on that chart that yes, it was actually pairs of stars that they were using for the longitude solution. And so look here, this is
Let's blow up the latitude and longitude lines of the Earth and stretch them out to the air.
That got it because this is Polaris, so it should be the pole should be here. This is our zenith, and this is right ascension and declination. So this is drawing these with 90 degrees directly overhead. So there's two different ways to draw the lines. Is it for your position, at which point you can say we're this many degrees, Polaris is this many degrees above my horizon, or is do you draw a circle around Polaris with like that's north and this is the celestial equator. So hopefully I haven't confused you there with the last sentence.
Right now you're seeing Louisville, 9:30 p.m. from our home latitude, meaning Polaris is 38.25 degrees above the horizon.
So let's
Always.
see, 40 is there, yeah.
But let's, when I get fun with it, let's go to,
Typically go to some hemisphere one time. North Pole, way. Polaris is
there's
dead.
the North Pole, and if time runs, everything's circumpolar.
So now that is,
And 6 months of the year you won't see those because it's light. And 6 months of the year you'll see them all night long and all day long. Ecuador, so now we'll live on the South Pole. Oh, that's funky.
Yeah, they can be
The
good.
South Pole people don't get to see the North Star
Well, unless they drill it.
unless they got a really clear horizon. 11:30 tonight on the equator. Or, not, we're in the south, we're on the equator, yeah.
Yeah, this is, I can see
I
that.
didn't go this way.
The North Pole is right on the horizon.
So everything rises in the east and sets in the west. No little circles or big circles, everything's half a circle, east to west.
It's 212. Search for the southern hemisphere constellations, the south pole constellations.
University of Louisville has several telescopes in the area west of Brisbane, Australia. So when I go down there and get out of the car, everything's upside down. Orion is literally upside down. You'd have to bend over and look through your legs to see Orion look like it looks like here. There it is up there, upside down. Let's start time. Let's turn on some constellations. Look, that was reverse time.
So this is the South Pole. There is no neat South Pole star. So it gets a little harder to navigate, or at least, do the Boy Scouts, Girl Scouts version of navigation. So there's a triangle that you can sort of use, but it's harder to do. There isn't that many neat stars.
There's the big Hydra.
Oh, there's Hydra, okay. And there is Scorpio, there is the hook of, Maui's hook, or whatever you want to call it. It's pretty clearly a hook, right? So everybody sort of made that a scorpion or something. So these are the southern constellations, and so you notice that some of them are the ones that the Greeks and Romans could see, because they wandered far enough south, so they have stories about them. But then you get to the ones around the South Pole, and here's where it gets a little funky, because this is a sextant that didn't exist in Roman times. There's a telescope somewhere, and there is I think the smallest constellation is Table Mountain, actually. So there's a bunch that are clearly been filled in by British astronomers because they wanted the map to be complete, but the Romans never got that far south, so they basically never named these, and I think Table Mountain was the last one to be named somewhere in 1962. So we still have, there's sort of a complete set of constellations with official boundaries and everything, but in astronomy we barely use them, except when we want to say, when we want to talk to people about I found something really interesting in Virgo. So there is the Virgo cluster of galaxies, which is in fact in the constellation Virgo, just very far behind it. And so I like the fact that we've taken these sort of self-proclaimed drawings on the sky and put our own stories to them. And so I think that's been a very human thing. Every culture we know of has at least a few constellations and stories that they illustrate. So I like this connection to everybody's mythology. That said, you've already know that they're all at different distances. These are not physically co-located stars anyway. So, all right. Thank you all for coming. Thank you all for playing in the planetarium with me. And Drew, can you please leave the group assignments here on the technical station, and I'll take your answers to questions if you